B. Bungee jumping. Other than kinetic energy and gravitational potential energy, elastic potential energy is also involved in bungee jumping. Elastic potential energy is stored in the elastic strain as it is stretched. The more it is stretched, the more elastic PE it stores. Without air resistance, total energy still conserves. The GPE, KE, and EPE interchange during the motion. It starts from position 1. When the man was not jumped, at that time his GPE is 0. Kinetic energy and EPE are also 0. When he jumps down the bridge, his GPE becomes negative. His GPE becomes KE until the elastic strain is first stretched at position 3. At position 3, some gravitational potential energy becomes elastic potential energy, but he is still falling. The elastic strain cannot stop him yet. His KE is still increasing. Both the EPE and his KE are increasing, while his GPE, gravitational potential energy, is decreasing, becoming more and more negative. Before he goes to the lowest position, something more happens. Just now was situation B, when the tension is still smaller than his weight. He is still accelerating downward. The speed is still increasing. Later on, he falls lower. The elastic strain may provide a strong enough tension to decelerate him. He begins to slow down, but he is still falling. He is still going down. His kinetic energy decreases. His gravitational potential energy also decreases, but the elastic potential energy increases at that time. Until finally the acceleration becomes 0 and there is a maximum speed. Later on, when he falls even lower, the tension would be larger than the weight, and at that time he begins to accelerate upward. The tension pulls him upward, giving him an upward velocity, and his speed increases again. And now he is leaving the lowest one and becomes higher in position. The gravitational PE also increases as he rises. Theoretically, if there is no air resistance, he may return to the bridge. At that time, the strain is no longer stretched, and so no EPE and his GPE should also be 0, and so his KE must also be 0 as well, since the total energy should be 0 at that time, the same as that at position 1. In example 8, Edwin goes bungee jumping. We may calculate the GPE by mgh, KE by half mv square, and then apply the conservation of energy to calculate elastic potential energy EPE at different positions, as in part B here. Try check point 4 on the next page. Three examples. Sum of kinetic energy and potential energy not constant. Of course, we can never get rid of air resistance and friction. In most cases, there is work done against resistance, and so the total mechanical energy decreases during motion. The following examples involve a high percentage of energy loss due to resistance force. The work done against resistance force cannot be neglected. The mechanical energy decreases with distance. However, the total energy still conserves. A. Braking. When the car brakes, the kinetic energy of the car is converted into work done against friction. In other words, becomes internal energy, so that the brakes, the tires, and even the road get hot. Their internal energies are then lost to the surroundings as heat loss. The picture here shows the skid marks when the wheels are locked and the tires slide on the road to brake. The length of such skid marks is the braking distance of the car. The work done against friction, Fs, is directly proportional to the braking distance. A plot of work done against friction versus displacement S gives a straight line of positive slope, while kinetic energy changes linearly with distance S, represented by a straight line with a negative slope. As there is no GPE change, the change in kinetic energy is the change in total mechanical energy of the car. However, if the deceleration is uniform, the speed decreases linearly with time, and hence v square wheel decreases along a curve, and so does the kinetic energy. The work done against friction, on the other hand, increases along a curve, and the sum of kinetic energy and work done against friction equals the initial kinetic energy, the initial total energy. In example 9, the energy change of an emergency landing of a plane is investigated. The situation is a simple conversion of kinetic energy to work done against friction. B. Roller coasters. A roller coaster is a good demonstration of interchange of kinetic energy and gravitational potential energy, and it also includes work done against friction. Usually, a roller coaster is first pulled to a high position so that it may start its subsequent motion with a lot of gravitational potential energy. The roller coaster may then swift along the rails. The work done against friction, W, is Fs, directly proportional to the distance traveled. The GPE, gravitational potential energy, equals mgh, directly proportional to the height, and the kinetic energy is just the energy left, which equals the GPE loss minus the work done against friction. In example 10, you can see how we may apply the principle of conservation of energy, and in that case, we have that equation. The PE loss equals the KE gain plus the work done against friction. C. Diving. A diver jumps from height. His GPE loss from the platform to the water surface changes to his kinetic energy just before he enters the water. When he enters water, his height is still decreasing. His GPE continues to decrease while he is stopped by air resistance, and so his GPE loss will all becomes internal energy of water, which makes the water in his body a little bit hotter. In example 11, you may apply the above principle to find how deep the diver may go when she jumps from a 10-meter platform. Nevertheless, you should note that the net force acting on her inside water is 2,800 minus weight, as her weight still is on her when she is underwater. So be careful whether the question mentions average resistance force by water or net force underwater. The two terms refer to different things. In exam length 1, there are two connected bodies. Y runs down an inclined plane. The GPE loss of Y will eventually become kinetic energy gain of X and that of Y, and also work done against friction. Take a look of part C in particular. and then try check point 5 on the next page.